CSIS 2430 is filmed before a live studio audience.
Last time we spoke, we talked about permutations, right? How many ways can you permute something? How many ways can I rearrange something? And the whole thing that we've been talking about for the past couple days, arranging things, that idea is called combinatorics. It deals with permutations, it deals with combinations, it even deals with graph theory. It's just the study of arranging things, which seems like a silly thing to study, right? But the applications are huge, right? So one of the main difference we need to make sure we understand with permutations, what we talked about the other day, order matters. I'm asking you how many ways can I rearrange something. And so if I have 3 cards, ace, king, queen, and I rearrange them to ace, queen, king, that's a different order, right? That's a permutation, which makes sense. I think we know that word kind of intuitively, right? That's, you permuted the order. With a combination, the order does not matter. So ace, king, queen is just the set of ace, king, queen. The order is irrelevant, okay? And we're going to see problems that deal with this in a few minutes, right? So again, with combinations, order does not matter. So what's listed here, these are the permutations of the set ABC. I think we'd all agree that that's every way you can arrange that, right? ABC, ACB, so forth, okay. Well, when you're dealing with combinations, the combination of that set, ABC, is the same as ACB, it's the same as BAC, and so forth. And think about when we deal with sets, right? That's exactly how we treat a set, that there's no difference. Like whatever order the set is in is irrelevant, okay? So this will play in a few minutes when we look at how we can do some choosing options and some choose problems, some combination problems, okay? And again, the idea is there's only one way to combine the letters A, B, and C. That's why we call this a combination. There's only one way to combine those letters, right? If I want to reach in and grab the letters A, B, C out of the alphabet, there's only one way to do that. I grabbed A, B, and C. Anything else is not grabbing A, B, and C. Doesn't matter if I grab C, B, or A first. That just the fact that when I'm done, I have those 3 letters. There's only one way to do that, right? All right. So how many combinations of any 3 letters of the set A, B, C, and D? And I'm not, if you think you know, we can talk about it, but I'm not, my intention wasn't to necessarily get you guys to answer it because I haven't really explained this yet. So let's just kind of walk through one, okay? So we can combine A with B and with C, right? Or we can do A with B and D, and so on, okay? A, C, D, B, C, D. There are only 4 ways to choose 3 letters from a set of 4. There are only 4 ways to choose. Think of it this way. I need to choose a subset of that set that contains 3. There are only 4 subsets that contain 3 elements. Does that make sense? Good? Okay. Here's a way to look at it. My question would be, how, if I wanted you to choose either the red, green, or blue balls, if I wanted you to choose those, what would you do? If I said to choose 3 of them, how many ways are there to do that? Just one. You just grab all 3 of them, right? Just one. If I wanted you to choose 2 of them, how many ways are there to do that? So you can choose those 2, or those 2, or those 2. That's it. There's no other option. If, again, you have a bag that just has 3 balls in it, you're supposed to reach in and grab 2. There's only 3 ways that'll turn out, okay? Because order doesn't matter. How many ways are there to choose just one? Also 3. I can either choose the red one, or the green one, or the blue one. How many ways are there to choose 0? There is one way to choose nothing. It's the only way, you just don't choose it, right? Okay, now, just yes or no, don't blurt it out, but just yes or no, do you recognize that pattern of numbers? Don't say what it is if you recognize it, but do you recognize it? Anybody? Okay, good. I'm going to save it as a surprise for next week then, okay? We'll see this pattern over and over again, okay? New question. How many ways are there to choose 2 of the following 3 letters? And again, think about what's really being asked here. How many, essentially I'm saying, how many subsets of ABC are there that only have 2 elements in it? That's what I'm really asking, right? I see somebody holding up their hands with 3 fingers. Yeah, Nate is. Well, So how many ways are there to choose two of the following three letters? Starting with 3 permute 2, let's look at what happens here, okay? We get this equation from the other day, remember? Remember that? If I were talking about permutations, right, 3 permute 2, you would get 6. But there's going to be duplicates there when we're dealing with sets, right? There's going to be some set AB and another set BA, but those are the same set. But if we just did a permutation, we would get that result, right? Then we divide out the number of times you can permute two things. So what we're doing here is I'm sort of giving you an insight into why the combinations formula works, which we're going to see that formula in a minute. So if I divide out the number of times you can permute two things, why do I divide out the number of times you can permute two things? So because the subset has 2 in it, right? And there's however many ways you can permute two things, which is just 2 factorial, right? Just like our little problem set we did the other day with the word fool, you can rearrange fool 4 factorial ways. But for that total of 4 factorial ways, there will be duplicates of the positions of the O's because it's the same letter basically. So we divided out the number of ways I can permute the O's, which is 2 factorial. Okay, so we looked at this idea the other day, right? So we divide out 2 factorial. So what we end up with is 3, and as you pointed out a second ago, Nate, that is the answer to how many ways I can choose 2 out of those 3 letters. How many subsets have 2 letters in it? Okay, so let's break this down a little bit. We started with this, 3 permute 2. That's every way I could do a P NK function, right, or NPK, right? Permute 3 items 2 at a time, right? That's what we did the other day. Those are all the ways. Would you agree? Okay. But how many ways can I permute each of those 2 things? Well, again, if we're doing a permute 2 of 2, or 2 at a time, we'll find out that those are duplicates of each other, right? AB is the same as BA, CA is the same as AC, and BC and CB are the same thing, right? So that's the 2 factorial we're talking about there. So when I'm talking about order not mattering, we have to divide out all those duplicates, which is the other half of our sandwich problem we did the other day, right? The sandwich problem was taking into account some duplicate sandwiches. We're going to talk about that in a few minutes, all right? So now, how many ways can I rearrange 2 things? Why 2 things? Because I'm looking at there's 6 sets there, 6 subsets there, A, B, B, A, C, A, and so forth. Well, I want to divide out the duplicates because in a combination problem, the duplicates we don't care about the order, right? So the duplicates need to be removed. So we dividing out the permutations removes those duplicates. All right, so here's a generalized formula for this that'll kind of make sense of what's going on here. Starting off with the number of ways you can choose k items from n elements is written this way. N choose k, right? So our thing with the 3 balls a minute ago, I was basically saying 3 choose 1, 3 choose 2, 3 choose 3, or 3 choose 0, right? You can also write it this way. That is not a fraction, that is just an n above a k in large parentheses. That is also pronounced n choose k. And then this is a function that we use, which is just the choose function, and again, choose k items from n, right? So here's a formula. What's that formula? What's going on the top there? That's just a permutation, permuting n things k at a time, right? We did that the other day. And as we looked at this example a second ago with those A, B, C and all that, we divided out k factorial. What's k? It's the number of things that so n permute k, or permute n things k at a time. That k is the number of things that I'm permuting. So if I had the alphabet A through Z and I said, how many ways can I choose, or can I permute 3 letters of the alphabet? We would use that formula on the top there, right? It would be 26, 3 that we'd plug into there. That's the formula we looked at the other day, right? Which is that formula right there on the top. Remember that one? The permutation formula is n factorial divided by n minus k factorial. You guys remember that? Okay? But then we're saying if we're going to deal where we don't care about the order, we have to divide out k factorial. Do you agree with all of that? We're moving, the second bullet point there is the combination formula that we just looked at a second ago. We all good on that? I'm not seeing nods from everybody. No? I got a nod, negative nod over here. Well, let's see where you're stuck. Do you want to back up? We can. So here's what I'm saying. Let's go back to the sample with choosing 3 items. We have 3 balls. We're going to pick one of them, or 2 of them, or 3 of them. Well, if I pick, let's say, the green and the red, picking the red and the green is the same thing, right? So if I were to count all of those ways, pick green, red, and also pick red, green, and then pick blue, red, and also red, blue, and then yellow, blue, and blue, yellow. If I were to count all of those ways, that's too many options, right? So I need to divide out all the duplicates. The duplicates will be those 2 items, the blue and the red and blue. That's the ways I can permute those 2 things. So if I divide out 2 in this case, is how many ways you can permute 2 things, then that gives us the unique sets of 2 items. Does that help? Okay. So that's what's going on in the second bullet point. All we've done is taken the permutations formula, and if I were to say, how many ways could you permute 3 balls 2 at a time? If I were to say, how many ways can you permute 3 balls 2 at a time? It would be 6, right? It'd be double the amount. But we're dividing out those extras because we want to know just what are the sets, not the orders. We'll look at some problems and it'll make a little bit more sense. But now, would you agree that bullet 3 is exactly the same as bullet 2? That's just algebra, right? Okay? Assuming we agree with the formula to start with, but let's say we do. Bullet 2 is the same as bullet 1. Bullet 3 is the same as bullet 2. So we end up with this. That is the same thing, just mathematically that's the same thing. What that is the combination formula, okay? So the combination formula says n factorial divided by k factorial times n minus k factorial. So let's look at some problems here and plug it in. What I'm saying here is 9 choose 4. If I had 9 quarters in a bag and I said for you to pick out, they all have different dates on them, let's say. If I said pick out 4 of them, it doesn't matter that you picked 66, 67, 68, and 69 in that order. As long as you've got those 4 quarters, that's one possibility. Make sense? All right. So 9 choose 4. You plug in the numbers with this formula here. Looks like that, right? Now, look closely at the denominator and compare it to the numerator. I'm going to do the math of what's in that parenthesis there. What pattern do we see here? The 2 numbers on the bottom added together equal the number on the top. That will always be the case. If those numbers don't add up to whatever's on top, you did something wrong in your formula, okay? So we plug in the values, and we're going to get those numbers. The point wasn't to calculate the numbers. The point was to make sure we understand that formula. So what this means is if I gave you 6 things and I told you to choose any 3 of them, there's only 20 ways you can do that. If I gave you 10 things and I said choose 6 of them, there's only 210 ways to do that. 9 choose 4. If I gave you 9 things, there are only 126 ways to do that. How many 5-card hands can be drawn from a standard deck of cards? Well, I'm just asking, if I have a deck of cards and I pull out 5 of them, how many different ways are there to pull out 5 cards, right? So let's start with this picture here. That is a full deck of 52. They're hidden behind the ace there, but that is a deck of 52. So let's just go with, I pulled out those 5, okay? Let's spread those out a little bit, okay? those are the same five. If I change the order, it's the same set of 5 cards that I pulled out of the deck. So I don't want to know that. I want to know just how many different exact specific cards can I have, how many sets that have exactly 5 cards exist, right? Now I could throw out that ace of hearts and put in an ace of diamonds, and now I have a different set, right? So that will be included in the calculation. So this is simply a 52 choose 5 problem. I have 52. How many ways are there to choose 5? Why 52? Because that's how many cards are in the deck, right? How many ways are there to choose 5 of them? There are 52 choose 5 ways to do that, right? We'll run the calculation in a minute. Does everybody understand that? Okay. So again, that's the exact same set. You don't count that multiple times. So the choose formula, the combinations formula, built into the calculation will automatically remove out the duplications. Because what we start off with was a 52 permute 52 5 at a time. That's how the combination formula starts, right? Permute 5 of the 52, which would be different because I want to know that, and then the 5 factorial ways I can do that, and then I want to know some other 5 card hand and the 5 factorial ways I can do that. That would be a permute problem, right? How many ways can I permute 52 things 5 at a time? That number's humongous. But we need to divide out that 5 factorial because it's a duplication of every 5 card hand, right? So 52 choose 5 is 2,598, right? You guys get that? And even if you calculated wrong, at least if you got 52 choose 5, you had the right idea, right? Okay. So now, next one, how many ways are there to draw a 5 card hand that consists of 3 diamonds and 2 clubs? Some information that you may not know about a deck of cards if you're not much of a card player. Every suit has 13, there's 13 diamonds, 13 hearts, 13 clubs, and 13 spades, right? So let's take a look at a hand here. This is one possible hand that fits the requirement, right? That question number 2 is asking how many of possible hands exist that have 3 diamonds and 2 clubs. That's what the question's asking, right? If I were to rearrange those cards, it's the same 3 diamonds and the same 2 clubs. Nothing changes. So that's one of the X number that exists, right? I'm not asking you what's the probability that you're going to draw that hand out. That's a different question. I'm just asking how many of these hands exist. How many hands exist in a deck of cards? If I were to pull out 5, how many different ways could I combine 5 cards to get something that matches this pattern? 3 diamonds, 2 clubs. All right, so take a look at these 3 diamonds here, right? Those 3 diamonds. For every set of those 3 diamonds, those exact 3 cards, king, 7, 3, I can pair them up with a whole bunch of sets of 2 clubs. I can pair them up with the jack and the 3, I can pair them up with the 10 and the 9, I can pair them up with the 10 and the 3, I can pair them up with the 5 and the 4, right? So we know that whatever the number of diamonds are, it's going to be multiplied by the number of clubs, right? So we need to figure out how many ways are there to get 3 diamonds, how many ways are there to get 2 clubs, then multiply them together. All right? So what's that look like? Well, if I want to know just how many combinations of 3 diamonds exist, there's 13 to start with. This is just a 13 choose 3 problem. Right? Does that make sense? I have 13 diamonds. I need to choose 3 of them. Any 3. How many different ways can I do that? Well, 13 choose 3, whatever that calculates out to be. Right? So you end up with 13 choose 3 times 13 choose 2. Because there are 13 clubs and I need to choose 2 of them. Right? Now, the word choose is a little iffy when you're dealing with cards, right? Because I'm not having you choose cards, and we're not calculating what's the likelihood you're going to choose one over the other. I'm just saying maybe how many ways could I line these up, or how many ways could I put this combination together? How many ways could I combine this? But would you agree that there are whatever 13 choose 3 is, there's that many ways to choose 3, that there's that many subsets of 3 cards from the whole set of all diamonds. The whole set of all diamonds is 13. 13, the cardinality is. There are 13 choose 3 subsets of that have exactly 3 elements in them. Do you agree with that? Yeah? And the same with the clubs. There are 13 in the original set that we're choosing from, and there are only whatever 13 choose 2 is, number of subsets that have exactly 2 cards in them. Multiply, do all the math, and you'll get that number. Okay, so questions about that basic idea. And by basic, I don't mean simple. I just mean the foundational idea is what I really mean, okay? We good? So here is finish the sandwich problem here, all right? So I think I want to give you guys a chance to figure this out now that you know what you know, right? This is the problem we did the other day, and the next few slides will walk through the final solution, but I want you guys to take a minute, and I'm only going to give you like 5 minutes on this because it's a very similar problem to what we just looked at, right? But it's slightly different, okay? And I want to see if you guys can figure out where, if anywhere, we need to apply combinations versus permutations versus just plain old addition rule, plain old product rule. What goes where, right? I'll give you guys a few minutes to work that out, but this is the rest of the story from the sandwich problem we did the last time we met. All right, let's look at the first one there. Number 1, the 1 bread, 1 meat, 1 cheese. Because we're just looking at 1, there really is only 3 choices for the first one. Now you could do 3 choose 1 and 5 choose 1 and 6 choose 1. But what's that ultimately end up being? 3 and 5 and 6, right? Okay. So that ends up being exactly the same as it was the other day. 3 choose 1 is 3. 5 choose 1 is 5. 6 choose 1 is 6. Okay. Does everybody see that? So that one's the same as what we did the other day. Next one though. We started off with 3 and again that's 3 choose 1, but we all agreed that that's just 3, right? And then we looked at what do we do here, right? And we came up with 5, 4, 3, right? You start off, you have 5 choices, and then once you pick one, you're down to 4 choices, then you pick one again, down to 3 choices. That multiplied out to 60, and we did the same thing with the cheese, right? And we ended up with 30, okay? But there's an issue there, right? We have to divide out the duplicates. So that ends up being 5,400, except that counted bacon, ham, and turkey as the same thing as a different sandwich from ham, bacon, and turkey, right? So let's take a look at a little picture of this. We got some delicious meats here. We have some beef, some turkey, some bacon, some chicken, and whatever you think that is. Mystery meats. All right. Yeah, weird shaped pineapple. And here's our 2 pieces of bread. Okay. So let's say that we decide to choose, well, we have 5 choices for their first meat, right? So we choose a cow. That goes on our sandwich. We choose beef. We now have 4 choices, right? And you can see the 4 at the top of the screen there. So let's say we choose bacon. Now we have 3 choices, and we choose mystery meat. There's our sandwich. Delicious, right? Now let's do another sandwich, okay? Let's say we got 5 choices like we did before. This time I choose bacon. Now I got 4 left, and I choose mystery meat. And now I got 3 left, and I choose beef. That's our sandwich. That sandwich and that sandwich are identical. It's the same sandwich. You go to a deli, they don't stack the meats in a different order and say, oh, that's a different sandwich on our menu, right? The other day we said that was the case. We didn't finish because we haven't learned about this idea here. So we have to divide that out. Well, what do I divide by? We divide by how many ways there are to rearrange what's on the sandwich. How many ways are there to rearrange that? 3 factorial, right? Which is 6. There are 6 ways to rearrange any given 3 things. So this is one of the 6 ways. That's another of the 6 ways. And of course I could do the other 4 if I wanted to, right? So we have to divide that out because that's all the duplicates. We divide that out, we'll have the correct number. So we take our 5400 that we had there, and what are we really dividing out? We're dividing out the 3 factorial, that's the duplicates on the meats, and we also have to divide out the 2 factorial, which is the duplicates on the cheese, right? Because we're choosing 2 cheeses. Everybody follow that? And then that ends up being 450, okay? Feeling all right about that? Okay. I don't remember if I put the numbers in here or not. I think I did, yeah. So if we start off with 13,500 and you divide out the 3 factorial duplicates and the 2 factorial duplicates, you'll get 1125. Right? Feeling all right about that? Now, there's a weird little subtle issue here. If I were to have applied the formula of 3 choose 1 times 5 choose 3 times 6 choose 2 for number 2, that'd work just fine, which a lot of you did exactly that, right? But by looking at problem number 3, it seems like that's the same thing. 3 choose 1, 5 choose 3, 6 choose 2. Why is it not? Why does that formula, the formula doesn't actually work in that scenario? Why not? Because we're allowing duplications, right? This is kind of like our problem with the table, sitting people around a table. How do we feel about that? This is why I don't like you to just memorize the formulas. Because if you just memorize the formula, you're going to run into snags like this where it doesn't quite work the way you want it to, okay? So in this scenario, it was easier or better to calculate the actual number, including the duplicates, and then divide out the duplicates, which brings me to a very important principle. Sometimes in counting, i.e. combinatorics, rearranging things, sometimes in counting, it's easier to count the stuff that you don't want and subtract it out from the set of everything, including the stuff you don't want. Sometimes it's easier to do that. Count everything, knowingly counting duplicates, and as long as you're doing it in a controlled way where you know that you're counting duplicates, then subtract out the duplicates. Sometimes that's a better way to do things. And that's a very important principle when it comes to this kind of stuff. Sometimes you got to do it that way. Okay? How do we feel about that? So let's take a look at another fun one here. This is going to mix up a whole bunch of stuff we've talked about now. Now, I'm going to use the word words very loosely here. And what I mean by this question, how many words with no vowels next to each other can be made from the word Tallahassee? I mean, using all of the letters. So, yeah, you can make the word tall, but I'm not talking about that. I'm talking about, like, whatever, 11, however long it is, 11 letters. How many 11-letter words, or whatever the length of Tallahassee is, can I make? And not everything's going to be a real word, right? But we're going to pretend that it's a real word, so just rearrangements is what I'm asking here. Everybody follow what I'm asking? Okay? All right, so how do we approach this problem? So it's like the other day when we did the problem with the word composition. The difference was we didn't care where the vowels had to be placed. We could just put them anywhere. Well, now we're being a little bit more specific. I want to make it to where no vowels can be next to each other. So that we have to divide out some extra stuff here, right? So let's break this down in baby steps. What are some things we need to consider here? Forget about the formulas and the calculations and the counts. Just what are some general, like our deck of cards example. One of the things, yeah, with the number of letters, right? In our deck of cards example, we had to figure out how many of each suit exist, how many cards are in the deck. In this case, we need to know how many letters in Tallahassee. What else? How many vowels we have, therefore also how many consonants we have, right? How many positions can even exist for a vowel to go, right? A bunch of things like that. So let's walk through these. So also we need to look at the duplicates, right? We have 3 A's, 2 L's, 2 S's, 2 E's. So let's just ignore the vowels. This is one of those scenarios I was talking about where just you can count it a piece at a time and do it in sort of in baby steps, right? So these are the consonants. There are 6 of them, right? So first question, how many ways can that be arranged? So this is a 6 permute 6 problem, right? Let's just start there. How many ways can that be arranged? Just mathematically, don't calculate, but just what's the 6 factorial divided by what? 2 factorial times 2 factorial, right? Because we got duplicate L's, duplicate S's. Right, so let's just make sure we follow that, okay? Does everybody understand what's going on there? So 6 factorial is 24, divided by 2 times 2, basically, which is 4. So there are 6 ways that you can place those without having any duplication. Agreed? Okay. Now, once I have those 6 ways, how many places can I position a vowel? This is like our dog and cat problem the other day, where can I put it so there's no cats next to each other, right? So where can I put the vowels where there's no vowels next to each other? Yeah, I could put a vowel here, here, there, 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 and there, and only one vowel. And how many spots is that? 1, 2, 3, 4, 5, 6, 7. Right? So I can place a vowel in 7 different places. Okay, that's the starting point. This isn't quite the answer, though. This is part of it. But this, we only have how many vowels? We have 5 total vowels, right? But yeah, there's going to be some duplication there. This problem is going to compound. It keeps getting worse, right? So let's start off, though. We have 7 places to position those vowels. Okay. So thus, where I can exactly put the vowels, I have to choose 5 of the spots to put those 5 vowels, right? Out of the 7 choices I have. Does that make sense? Right? I have 7 spaces. I need to put vowels in 5 of those 7 spaces. How many ways can I do that? 7 choose 5 ways, right? And how many ways can vowels be ordered? How many ways can I rearrange the vowels? 5 factorial divided by 3 factorial times 2 factorial, right? To get rid of the duplicates. Like that? Now, I'm giving you little bits and pieces of this. We're going to put the puzzle together in a second. But do we agree with everything I've said so far? Is anybody unclear why I've said it? Because you can agree with me but not understand it. That's a different story. We can talk about that. Feeling okay? Okay, so let's continue on here. Look at this choice down here. LSHTSH. That is one of the 6 ways I can rearrange those letters without having any identical looking patterns, right? 6 different unique ways. That's one of the 6. We established that there were 1, 2, 3, 4, 5, 6, 7 spots to put the vowels, right? I didn't mean to cover that H there. But there are 7 spots to put the vowels. Well, I'm going to place them in 5 of those spots. I'm going to choose those 5. That's a 7 choose 5. How many different ways can I do that? Because I can move those 5 all over the place, anywhere I want, right? But I chose those particular spots. I could have chose those 5, right? I could have chosen those 5. There are 7 choose 5 ways to do that. Agree? Okay. So now let's put the actual letters in there. Of the 7 choose 5 locations, I can permute that list 5 factorial divided by 3 factorial times 2 factorial. Right? That's how many ways I can permute 5 things and eliminate the duplicates, right? So in other words, watch this. If I rearrange this, that's the exact same pattern I had in the previous slide, right? That is the same thing as that. So I need to divide that out. That's where the dividing of the 3 factorial comes in, because I'm dividing out all the duplicate positions of all the A's. Dig it?
I dig Sugar Smacks.
I could do that. That's still the exact same word right there. Right? I just rearranged it. So that's why we need to divide out the 3 factorial times the 2 factorial. It's the exact same thing. All right, so if we go to the next slide here, we'll see that 6 factorial divided by 2 factorial times 2 factorial calculates to be 180. What that means is that there are 180 ways to arrange TLLHSS without any duplicates, like identical ones. Like TLLHSS is the same as TLLHSS. We're ignoring that duplicate, right? A minute ago I said that there were 6 ways. That was just me calculating wrong in my head, sorry about that. I was thinking that 6 factorial was 24, but it's not, 720, right? Sorry about that, okay? Next up, so we figured out there are 180 ways to rearrange the letters of the consonants. How many places can a vowel be placed? 21. 7 choose 5 is 21. So I can pick 21 different positions to place those vowels, to place 5 vowels. 21 different ways to put 5 vowels in there, regardless of what those vowels are. There are 21 placeholders, arrangements to put the vowels. Does everybody see that? There are 21 different ways I can choose. I can choose the first vowel spot, the third spot, the fourth spot, the fifth spot, and the second spot, or I could choose 1, 3, 5, 6, right? There's all different ways. And then once I've chosen those 5 spots, one of the 21, there are 10 ways that I can rearrange the actual letters in those spots that will be identical with each other. So we got to get rid of all that, okay? So for each of the 101 ways the consonants, 180 ways the consonants can be arranged, there are 21 different sets of 5 spots to place the vowels, which is what I just said. For each of those scenarios, there are 10 ways to arrange the vowels into those spots. So there are 180 times 21 times 10 ways to arrange Tallahassee without having any vowels next to each other. We're dealing with everything in there, permutations, combinations, product rule, everything, right? And the answer is 37,800, right? What questions do we have about that? All right, here's another similar problem. Did we not do this problem yet? When I said cats and dogs a minute ago, you guys were like, what are you talking about, Jeff? Sorry, I thought we did this problem. Oh man, don't listen to me. I don't know what I'm talking about. So, with 6 cats and 4 dogs, or 6 dogs and 4 cats, how many ways can they all stand in a line? That's an easy one. How many ways? 10 factorial, right? I got 10 things, I want to line them up. How many ways can I permute them? That's easy, okay? How many ways can they stand in line with no cats next to each other? This is basically like the Tallahassee problem. It's not as complicated, right?
Line up the 6 dogs and then count the spaces between them.
Right, so line up the 6 dogs, count the spaces between them.
7.
So there's 7 spaces between the dogs, right? Or that the cats can be positioned.
So then we do 7 choose 5.
And we got to pick 4 of those spaces, right? So let's take a look at it like this. I got dog 1, dog 2, dog 3, dog 4, dog 5, dog 6. There are 6 factorial ways to do that. There's no duplicates because they're all unique dogs, right? Even if they were twins, they're still a physically different dog, right? Which gets you into gray area when you're talking about sandwiches, right? Because even though those 2 pieces of turkey are the same thing, then in that case, we do treat them as turkey 1, turkey 2 is the same as turkey 2, turkey 1 sandwich, right? But in this case, they are separate dogs, and we're talking about lining them up. And if I were to ask you how many different ways could I permute the meat on a sandwich, then you wouldn't divide out the duplicates. So there are 6 ways to arrange the dogs. And then there are 7 choose 4 ways to position a cat between the dogs or on the outside of D1 or D6, right? And then there are 4 factorial ways to rearrange those once they're in position. So I could choose, there's 7 spots, and here's my 4 I'm going to choose, those 4, right? I could have chosen any 4, and there are whatever 7 choose 4 calculates out to, there's that many places to put a cat. Once I've chosen that spot, I'm going to put cat A, B, C, and D there. But I could also put cat D, C, B, A, and B, A, C, D in those same exact 4 spots. So for every one of those 7 choose 4 things, there are 4 factorial ways to rearrange the position of which cat goes in those 4 things. So when all is said and done, we get 6 factorial ways to put the dogs, 7 choose 4 ways to place the cats between them, and then 4 factorial ways to rearrange those cats once we're done. That's 604,000. What about the third one? Yeah, it can't even be done. There's no way to do that, right? If I have 4 cats, there's only 5 possible places to put a dog. So I've got 6 dogs. That's a pigeonhole thing, right? The reason I show you that last one is not to trick you, it's just to let you know that sometimes you can see kind of an obvious answer before you really run any formula on it, okay, if you break it down to baby steps. So the question here, how many binary strings contain exactly 5 zeros and 14 ones, where each zero must be preceded by 2 ones? Let's take this back into baby steps. What if I didn't give you a restriction? If I just said, can be preceded, I forget about the part about preceded by 2 ones. I just said there are 5 zeros, 14 ones. What would the answer be? Well, correct. Now let's imagine that each of those were different things. They weren't just ones and zeros. It's 14 different or 19 different things. It'd be 19 factorial, right? But because 14 of them are exactly the same thing, having 14 ones in a row is the same as having 14 ones in a row that are different ones, right? So you have to divide out how many different ways you can rearrange 14, right? And you'd have to divide out how many ways you can rearrange 5. So it'd be 19 factorial divided by 5 factorial, also divided by 14 factorial, if we didn't have this restriction, right? So how many total permutations are there? Again, permutations, it would be 19 factorial divided by 5 factorial divided by 14. That is the number of ways I could permute that list without having any identicals. You guys agree with that? Without the rule, without that little stipulation. All right, okay. Now, with this, we know that we're supposed to have 5 zeros and 14 ones. But we also know that these are the only types of patterns that can exist. If I have a 0, there has to be at least 2 ones right before it. There could be 3 ones or 4 ones, but there has to be at least 2. So that being the case, there's no such scenario where there's a 0 that doesn't have a 1 immediately to its left and then another 1 immediately to that left. So there's no other way that a 0 can be arranged than this kind of grouping. So if we take all 5 of our zeros here and we tack on 2 ones for each one of them, we end up with these 5 patterns, which are identical to each other, and we end up with these 4, which are also identical to each other. So now what do we have? Yeah, we just have 9 things that can be arranged 9 factorial ways divided by the duplicates. Right? If I have 9 things and they were all unique different things, then it would just be simply 9 factorial. Right? So the final calculation, though, it's 9 factorial divided by 5 factorial, which is the duplicate 110 sets, and then divided by 4 factorial, which is the duplicate 111 sets. How do we feel about that idea? Is that a little bit clearer? Okay, let's take a look at another one here. There's 3 questions to be answered here. Using the set of letters, that set right there, answer the following questions. How many permutations of the set are there? How many of the permutations start with a K immediately followed by a vowel? And how many 3-letter words that are consonants, how many 3-letter words that are consonant, vowel, consonant in order? How many 3-letter words can you create that are in that order, consonant, vowel, consonant, right? And we are not allowing duplicates here, right? So use a letter once and it's over. Got to understand the questions? All right, go for it. So example number 4 here. We have the set of the letters Z, X, V, K, R, A, J, E, I. How many permutations of the set are there? 9 factorial, right? How many ways can I rearrange it? That's it. Easy enough, okay? How many of the permutations, so of those 9 factorial, how many of them start with a K and then are immediately followed by a vowel? So how do we walk through something like that? We start off with the first blank field, right? In fact, I'm going to pull up it's like a spreadsheet here and sort of try to mimic this. So I hear this question a lot. You asked it a second ago, Amanda, and a lot of people ask this question. Sometimes the formula doesn't work. How do I know when to use the formula? How do I know which technique to use? And that's not an easy question to answer, frankly. But generally speaking, the way I approach this is I start with this idea of making blanks. There, now we can play around with it. So my approach is this. Make the lines. Now, if you have it's asking you 100 and you have to make 100 lines, no, don't do that. But make 10 lines and see what it would look like with 10, and then just see if you can follow the logic and figure out how to calculate it, right? So the first set here, where it's supposed to be a K, the first letter has to be a K. Well, there's only one way to do that, right? Agreed? So that for no matter what, it's going to be a 1 there. Let's center all this here so we can, there we go. The next letter, it has to be a vowel. Well, how many vowels are there? There's only 3, right, in this particular set. So it has to be 3 there. There's only 3 choices you have. Now with the remaining, there's a total of 9 values, 9 in the set. 2 of them are already used, right? So 7, 6, 5, 4, 3, 2, 1. Multiply those out and you have your answer. I think everybody got that and it makes sense, right? And some of you wrote 1 times 3 times 7 factorial or just 3 times 7 factorial. All of those are correct mathematically, right? All right, how do we feel about that one? Pretty good? All right, let's clear that out. And I think that's the next thing on the slide there, yep. All right, let's look at the last one here. How many 3-letter words that are consonant, vowel, consonants can exist? So we don't need to worry about any of those. I'll just change their color to orange or something, just ignore those, okay? We'll just focus on these. How many 3-letter words that start with consonant, then vowel, then consonant? Well, how many consonants do we have? We have 6. So we have 6 choices. How many vowels do we have? 3. How many consonants do we have left to choose from? 5. That's it. The answer is 90. Well, I thought I had 90 on the screen. I guess I didn't. Okay, pretty straightforward. If you try to plug in a formula there, there's not really none of, the only one where the formula might have worked is number 1. That's a 9 permute 9 problem, right? So you could use the permute function, the p parenthesis 9 comma 9, and plug it in the formula, which is n factorial divided by n minus k factorial, right? But what's the point, right? Okay, so it's easy enough to calculate it by starting here. Sometimes when you start here, you'll end up actually using the formula just coincidentally. Sometimes you won't be able to use the formula at all because it won't work. And so that's why I prefer just thinking about it intuitively, okay? Some of them are blatant. If I said, how many ways can you choose 5 things out of this set of 20? Well, that's a 20 choose 5 problem. It's pretty blatant, right? And you can just plug in the formula if you want. But even that you can do, sort of draw it out on paper, okay? Questions on that one? Take a look at the next one. Using X, Y, or XYZ graphs without allowing backtracking, answer the following questions. How many paths are there from 2,8 to 711? And how many paths are there from -2, 0, 8 to 4, 5, 10? All right, how many paths are there from 2, 8 to 711? Look at it this way. I'm trying to get from x2 to x7. No matter what I do, if there's no backtracking, let's say there's no left-right backtracking, no backtracking on the x-axis, then I'm guaranteed to make exactly 5 moves from the point I'm at to the point I'm headed to, if I'm just talking about the x-axis. Agreed? Does everybody see that? That's true? Yes?
Yeah.
Yeah, just want to get a nod from everybody, right? All right. Then, even if I were allowed backtracking on the y-axis, so I went down to -5,000 and then eventually made my way back up to x7, right? -5,000 on the y-axis. I eventually make it up to x position 7. I still only moved from 2 to 7 on the x-axis. That's only 5 spots, right? All right, same thing is true with 8 through 11. It's only 4 spots. I can only, or sorry, 3, yeah, thank you, 3. I can do math. Only 3 spots, thank you. Right, from 8 to 11, that's 3 spots. Okay, so that's a total of, because we don't allow backtracking, a total of 8 moves. Some of them are up, some of them are right. So that's 8 things I'm doing. That's 8 factorial, right? Agree with that so far? We're not done, but so far so good? Problem is, 5 of those 8 are the exact same move. It's a right. And 3 of those 8 are the exact same move. It's an up. So I just need to divide out the duplicates. 8 factorial divided by 5 factorial, because that's how many ways I can rearrange the 5 duplicates of right. and divide by 3 factorial, because that's how many ways I can rearrange the 3 duplicates up. So you end up with that. Next one, same exact story. I need to go from -2 on the x-axis to +4. How many changes is that? That's 6 just along the x-axis. And how many from 0 on the y to 5 on the y? 5. And how many on the z-index? I'll call it out from 8 to 10. 2. So what's the total of that? I didn't add that up in my head. That's 6, 13. So 13 factorial is the total possible scenarios where I could move, except for one of those scenarios will look exactly identical to another one, right? In fact, that'll happen 6 factorial, and then 5 factorial, and then 2 factorial times, right? So we need to 13 factorial, but of that 13 factorial, 6 factorial times 5 factorial times 2 factorial are identical to each other. So divide those out. Why is it 6, 5, and 2? Because 6 is the number of ways I can rearrange the different rights for moving along the x-axis. 5 is the number I can rearrange the y's, the going up, and then 2 is the number of ways I can rearrange the z, going out or in, or however you want to look at it. Okay? If you go back to the previous video, we do a problem like this, and I actually had draw a graph on the screen, and I animated a little bit so you can kind of see what we're doing, and it makes a little bit of sense, a little bit more sense. Okay? Feel good about that one? Next up, using the 7 letters in this set, that's A, B, C, D, E, F, I, how many ways can they be arranged if the first 3 must be consonants? All right, let's take a look at this one here. Using the 7 letters in the set, how many ways can they be arranged if the first 3 must be consonants? Well, how many ways can they be arranged if the first 3 must be consonants? B, C, D, and F. That's 4 consonants, right? So there are only 4 choices for the first. And I forgot to mention this is only no duplicates, because I shouldn't have to mention that because it's a set, right? But just in case, because there are some times where I may say you can use it multiple times. The alphabet's a set, right? But you can use it twice. Says the guy who's got 2 F's in his first name, right? All right, but in this case, we are talking about no duplicates. So next up, the next one has to be a consonant. So how many are left? 3. And then the third one must be a consonant, right? So 2. Now, the last 1, 2, 3, 4 there, how many choices are there? There's whatever was in the original set, 7, minus the 3 that we've already used, right? The fact that there's a 4 and a 3 and a 2 there has nothing to do with anything. That just means now we've used 3 letters. So what's left? There are 4 left, and then there are 3, and then there are 2, 2, and then, of course, the last one, right? Now, here's another one of those things that's a weird sort of coincidence. You could argue that that's 4 factorial squared, right? But that's a complete coincidence, right? You couldn't just apply that formula anytime you wanted to, right? That's just a coincidence that it turned out that way. So that's why I say be careful of just trying to plug a formula into it. The problem we did the previous slide with the graphs, coincidentally, using the combination formula would have given you the correct answer as well. And maybe that's correct, maybe it's a coincidence, but it's not intuitive either way you look at it, right? All right, so whatever that math works out to be, but those are your values. And I don't have the answer there, but if you calculate it, I'll just trust that you got it correct, okay? All right, now what? How many numbers can be formed? This one's trickier. This will take a little bit of extra time here. How many numbers can be formed using the digits 5, 6, 6, 7, 7, 8, 9, if we want each number to be greater than 7 million? Okay? So now, before you guys dive into this, I want you to think about this, and I mentioned this off camera a second ago. These are all combinatorics problems. They're all counting problems. Combinatorics is the study of arranging things, right? There's lots of ways to arrange things. There's lots of techniques. There's the pigeonhole principle helps you arrange things and figure things out. There's the addition rule, the sum rule, the product rule, I should say. There's combinations, there's permutations, there's graph theory, there's all kinds of stuff, right? So don't get stuck into one technique. Just use whatever technique works as long as it's accurate, and you're gonna find that you're gonna have to use a couple of ideas here to get this one to work, all right? So I'll leave you to it. All right, so let's take a look at one approach, all right? In this case, we can use multiple different things that we've looked at. Here we have 3 different cases. I have a case where some number starts with 7, or starts with 8, or starts with 9. 7 point something million, 8 point something, and 9 point something, okay? There isn't a 4th case that also starts with 7, right? Even though there are 2 7s in the list of numbers there. Because that's just the same thing, right? So we're not gonna bother with that. But now that I have this one scenario of starting with 7 or an 8 or a 9, now what? Well, we've used up one of the numbers, right? So once we've used up one of the numbers, then we could just fill in the rest. So what's it gonna end up being? It's gonna be 6 factorial, right? Let's go back to our spreadsheet here. And this is a 2, 4, 6, 7-digit number, which I believe is how many I have blocked out here. And so the first scenario, there's only one way, one way to get a 7, right? And then, or one way to get, we're gonna pick the 7, right? And then the rest of them, there's gonna be 6 letters left, or 6 numbers left. So 6 there, 5 there, 4 there, 3 there, 2 there, 1 there, and that's it. That exact same thing's gonna happen when I put 8 as the first number and when I put 9 as the first number. Agreed? So each of those scenarios, it's 1 times 6 factorial, which is just 6 factorial, okay? So we get 1 times 6 factorial, but now we have to divide out 2 factorial. Why? Because we have 2 6s, right? But we also have 2 7s, right? But we already ignored those because we're only using that, counting that as one case there, and we're not counting the 7 scenarios twice, right? How about the 8? It's going to be 1 times 6 factorial divided by the 2 permutations of 6s divided by 2 permutations of 7s, right? And then 9, it's going to be the exact same formula, dividing out the 6s and the 7s. You add all that together, 360 plus 180 plus 180, and you get 720. Sorry, I thought I had that on the screen. All right, good? How do we feel about that? Fabulous. All right, so that's the last of the examples here in the PowerPoint. We will do some more in a minute. But first, let's remind ourselves, why do we care about this stuff? I keep telling you about it. I keep teasing it. We will get to it eventually. Why do we care about this stuff? It's because of probability, okay? Why do we care about probability? Why do we as computer science people care about probability? So yeah, it's used in machine learning. A perfect example of this, one of many, the Google self-driving cars that give us Google Maps, those are run on probability, believe it or not. Self-driving cars, even the ones that are eventually, I think there are already some on the market right now. There's some self-parking cars, right, that can do parallel parking and this kind of stuff. That stuff is all probability. So there's in the Google self-driving cars, and I think I mentioned this before, but they look at objects that they can see in front of them, and they have to be able to recognize, is this something that's dangerous, or is this something that can harm the car or harm a person if I ignore it or run over it or whatever, right? So in other words, if a little rodent scurries across the road, do they just keep driving, or do they stop for the rodents? Are they smart enough to figure out that it's going to cross the street and by itself and probably not get hit? All this is probability stuff, okay? Probability is a simple equation. It's the favorable outcomes divided by the possible outcomes. What's a favorable outcome? If I'm rolling a die, or I'm rolling 2 dice, and I want to know what is the probability that I'm going to roll, let's just say with 1 die, what's the probability I'm going to roll 3? It's 1 out of 6, right? The 6-sided die, assuming it's not loaded, 1 out of 6, okay? It's super easy. But complex probability comes in where I don't know what the favorable outcomes number is. hence I have to apply counting techniques, combinatorics and things like this, permutations, combinations, this kind of stuff, to figure out what is the numerator and how many possible outcomes are there. I have no idea. I have to calculate it sometimes. Sometimes it's easy. 1 out of 6 for a die, easy. So we're not going to get into the poker hands today, but we will next time, maybe 2 times from now. If I wanted to know what is the probability that I'll get a full house in a regular deck of 5-card poker, no draw, let's just go stud, what are my numbers for my numerator and denominator? It's some number divided by some number, that's it. But what are the numbers? That's a hard question. Well, the possible outcomes are how many possible full houses even exist, right? How many different full houses are there? So let's go with clubs, hearts, spades, aces, and the 2 black kings. Well, there's also clubs, hearts, spades, aces, and the 2 red kings. There's also club and heart red, kings, and then there's club and diamond. There's all these different ways to do that. How many of those exist? That's the possible outcomes, right? Or sorry, that's the favorable outcomes of full house. How many of those exist? How many possible outcomes? Well, how many 5-card hands exist? If I took a deck of cards and I dealt out 5 cards, how many different ways can that exist? That's actually not a hard problem. That's 52 choose 5. That's it. That's your denominator. But the number of actual full houses that exist, you have to calculate that. It's harder. Okay, and we'll do some problems like that in a couple days. All right, so we care about probability because of things like Bayes' theorem. That's what's called conditional probability. Given that event A occurred, what's the probability that event B will occur? Right, and we talked about that, and we will get into that in depth another day. But it's everywhere. It's spam filters is how it uses Bayes' theorem. And there's a whole bunch of other things. And I think I mentioned this to you before, but I'm going to pull it up on the screen this time. This is a few of the covers of it, a few of the versions of it. You see here for $10. This book is all about, the subtitle is it's Hello World, and then it's Being Human in the Age of Algorithms. There's some crazy stories in there about probability and how we rely a little bit too much on computers sometimes. There's a story in there of a guy that drove off of a cliff because the probability calculation it calculated the probability, but it wasn't good enough. It was still wrong. Even if it's a 99% probability, there's still the 1%, right? So a guy just followed what the Google Maps or whatever told him to do, and he drove off a cliff. There's another story in there about a guy who got beat senseless by the cops because his face matched an actual criminal that killed a cop. And so the probability that it was the same guy was high enough that the cops knocked on his door, tricked him into coming out of his house, and beat the crap out of him. Turned out he wasn't the guy who did it. It was all based on an algorithm, right? So that probability plays into a big part of our lives as computer science people. And it also plays into art. It plays into the legal system. There's cases in there about what's the probability that a criminal will recommit a crime if given the chance to get out early or stay in prison longer or whatever. All this stuff is calculated with probability, and there's all kinds of stories in there about situations where you have to find the balance between relying on the humans and relying on the probability. So it's important stuff. It's huge. But it all starts with being able to figure out what the heck goes on the numerator and what goes on the denominator. And those are not always easy things to answer, okay? Any questions about anything?